Hello everyone again. So here we have certain terminology regarding the pump. For example, here this is a pump here, and which is taking the liquid from the tank below the pump level, and then it's taking the water and it's going up into the duct, and then it is going into the upper tank level. So this is another tank where this tank is filling by with the help of pump. So whatever is the tank level below the pump center line, so this we call basically the suction lift. Suction lift from this point to this point. This is the suction lift, and whatever is the water level in the tank above the pump center line to the discharge tank we are talking about. So above the center line, so this height we call it discharge head. Discharge head. So there is one which is suction lift and another one is the discharge head. So the pump has to work against these two. Like the first is it has to take the water, and it has to overcome this much of lift, and then it has to deliver the water to a higher level, then it has to overcome this much of discharge head. So the total head of the pump is basically the sum of the two, this plus this part, and this we called it the total head of the pump. Similarly, when the pump is installed below the suction tank, so the suction tank water level is here, and the pump is here, so it is below by this much height. So this height we call it suction static suction head. So or simply we call it the suction head. So this is suction head, and this is the tank level, and which is above the pump center line, and it is above the pump center line by a certain height. So this height we call it the discharge head, this much. So when we talk about the total pump head, then already the suction tank has this much. So when we talk about the total, then this much should be subtracted from this total. So when we calculate the total we will calculate from tank surface to tank surface. So here from tank surface to tank surface, this is the total static head developed by the pump. These are the terminologies. So some other forms in symbolic terms, if we want to say like this is when the tank is below the pump level, so this much is the difference between the pump. Up here we are talking about not the tank, there is no discharge tank here. So here we are talking about only from the pump center line. So this much is below the pump center line, so this is, we are calling it the suction head, or we can call it the as not the suction head, suction lift, because this is the pump has to lift the water. So this is suction lift. When the tank is above the pump center line, as in this case, and this is the pump center line, so the pump is below the tank free water level, and whatever amount is this, so this is basically we call the suction head. Suction head, this is, this much is suction head. So the suction lift we are indicating by ZS, and the suction head we are indicating it by minus sign. So this should be, this is just the terminology that you have to remember. So here we have two points where our focus is concentrated. Like the one is the at the tank surface, so this is our point of one, and the second is at the pump inlet here, so which is our point 2. So if we talk about at point 1, the pressure is atmospheric pressure and the velocity is 0. And if we talk about at this point, which is at pump inlet, so the pressure, there will be some pressure which we don't know actually, and the velocity v2 will be whatever is the velocity in the pipe, that will be the velocity at the inlet v2. So if we set up the Bernoulli equation between this point and this point, then we can write that the pressure term at point 1, and the velocity term and the potential term, and at this section at 2, the pressure term, velocity term and potential term, and there are some minor losses like the inlet and the band, and there may be some other also. So the summation of minor losses, and there is a friction losses in this line, so this is the friction loss in this line. So we can set up the modified Bernoulli's equation in this form. Now we can simplify that. The V1 here, this is going to be 0, and V2 is basically the velocity in the pipe, and the P1 is atmospheric pressure. And remember that this is Z2 and this is Z1. So Z2 minus Z1, we will describe it as suction lift, and which is Zs. So this is Z2 minus Z1. So when we substitute these values into this modified equation, then the form of the modified equation can be reduced to this, that these are the two quantities. So basically you just keep these two quantities on one side and take all other quantities on the other side. So these are the quantities, so the friction losses and the minor losses and the pressure at section 1, and this is the potential difference. So here we will do something that, remember that this pressure P1 usually we take as atmospheric pressure because this is the section 1, and here the P1 means the P atmosphere. So normally we consider it as 0, but here in this case, because we are interested in cavitation and the cavitation occurs at saturation pressure, so we are not making atmospheric at 0 because the saturation pressure is absolute quantity. So we are not making it 0. So we are taking the pressure in absolute unit. So P1 is P atmospheric. So this is the equation that we can get after shuffling the terms from the modified Bernoulli equation. And then what we do, we subtracted this term, which is PV over rho g, from both sides. So here we have two terms, and then we subtracted this term also. So now on the left hand side you have three terms, and here we have this P1, so we subtracted PV over rho g from the right hand side also to balance the equation, and this Z2 minus Z1 is our Zs, and these are the two losses. So what is PV here? The PV is the saturation pressure. We call it the saturation pressure, or we call it the vaporization pressure. So this is saturation pressure. So you can get the equation in this form. So whatever is the quantity on the left hand side, these quantities we call it the net positive suction head available in the system. Net positive suction head available in the system. So which is P2, and P2, the point 2 means at the inlet of the pump here, point 2. So that means the pressure head at point 2, and this is the saturation pressure head at point 2. So this is subtraction, and plus the kinetic head at point 2. So the pressure head plus kinetic head minus the saturation pressure head at point 2. So this quantity we call it the net positive suction head available. So this quantity is in terms of these quantities like P1, PV, this. So if this we are saying it that this is net positive suction head available, so this is equals to this thing. So what we can understand from here, that if we want to calculate the net positive suction head in any of the system, like either this is one system and this is another system. So in any of the system, if we want to calculate the net positive suction head available, then what are the quantities we need? We need that the P1. The P1 means the pressure at here, so which is basically the atmospheric pressure. And we need the PV, saturation pressure. So the saturation pressure depends upon the temperature. So if we know that the temperature of the flowing fluid, then we can go to the thermodynamic table, and then we can find that what is the saturation pressure for this. And this is our design. From the design schematic we can see that what is this Zs. So the Zs is basically Z2 minus Z1, so that we can calculate from our design parameters schematic. And these are the friction losses and minor losses. So the friction losses, the velocity in the pipe, in the suction line pipe, which is this one, and this is the length of the suction line from the tank to the inlet of the pump, and this is the diameter of the line, and this is the friction factor. So we need to know the friction factor, and of course when we calculate the friction factor, we need to know that what is the Reynolds number and what is epsilon over d. So these things we need to know when we talk about the friction factor. Okay, so once we know the velocity and we know the diameter and we know the length, then we can calculate the uh, Reynolds number, epsilon over d, and we can calculate the friction factor. So if in any configuration or in any design, if these parameters are given, for example, the diameter of this line is given, the length of the line is given, and the fittings information is given, then basically we can calculate these terms, and we can substitute here and to find out that what is the net positive suction head available for this system. So you remember that when we describe the pump characteristic curves, and there we say that the net positive suction head required, and that comes from the graph, like this graph. So this curve indicates that what is the net positive suction head required. So corresponding to any flow rate, like if there is 80 liter flow rate in the pump, 80 liter per second, then it is touching the curve here, and then this line you take it to the right hand axis, and then you will touch it here. So let's say some 3.9 or 3.8 something is the this is the net positive suction head required. So this is the required by the pump, net positive suction head required. And what we are talking about here is the net positive suction head available in the system. So to avoid cavitation, the net positive suction head available in the system must be greater than the net positive suction head required by the pump. If it is not greater than, then the cavitation will occur. If it is less than the net positive suction head available, then the cavitation will occur. So to avoid the cavitation in any pump, then you have to make a check in your system. You first calculate that what is the velocity in your section line, what is the Reynolds number in your section line, what is the friction factor in your section line, and what is the length of this section line, what is the diameter of this section line, and what is this ZS, which is Z2 minus Z1, and the point number 2 is here. And then if it is taking from the tank, then what is the tank pressure? The tank pressure will be like if you're taking the point 1 at the free water level, so which is P atmospheric, and the PV corresponding to the temperature. What is the temperature of the liquid? And then you go to the thermodynamic table and then find out what is the saturation pressure, and then you substitute all these quantities and then find out what is the net positive suction head available, and then you will check with this that this is the pump requirement. If the system has more than the pump requirement, then it is safe, and if not, then the cavitation will occur. So I hope this is clear now. So now there are few points that you have to take care of. Our criteria is that the net positive suction head available should be greater than the net positive suction head required by the pump to avoid cavitation. And this is calculated using this formula. So in case if the net positive suction head available is not enough, then what should we do to make it more, or to basically make it more and above more than the net positive suction head required to avoid cavitation? So what are the quantities that can enhance this value, that can increase this value? So you see that this entire term is in negative, with negative sign, and this is also with negative sign. So first of all, you have to reduce the friction losses and minor losses from the section line, from this line. Reduce the minor losses and reduce the friction losses. So the minor losses can be reduced when you reduce the number of fittings, and the friction losses can be reduced if you reduce the length or if you increase the diameter, right? And this is from the loss, and Z2 means ZS is Z2 minus Z1. So what does it indicate? That, and this is with minus sign, this is with minus sign. So what does this mean? That the Z2 should be reduced, the Z2 should be reduced and Z1 should be increased. So Z2 should be reduced means that you have to bring the pump down, and Z1 should be increased means you have to increase the level of the tank or increase the level of the water. So you have to make the system like this kind, like you take the tank up and you bring the pump down to avoid the cavitation. Is it? So this kind of configuration has less chances of cavitation than this kind of configuration, because here in this case the Z1 is less and here in this case the Z1 is more. So the Z1, this minus sign and the minus sign this before, will make it plus, so it will add into the net positive suction head available. Okay. The second thing is that the P1 is the atmospheric, so you have no control over that. It's atmospheric pressure. Now if the PV, and this is with negative sign, so if you want this quantity to be more, then the PV should be smaller. This should be small. So how can you control that? It depends upon the temperature. So if you bring down the temperature down, if you bring the temperature down, then the saturation pressure will also come down as per the thermodynamic table. The higher the temperature, lower the vaporization pressure. So like as you go on, so so as the temperature is increasing, the vapor pressure is increasing. So as you can see from this table, like that. So higher the temperature and higher the saturation pressure. So at 20 degrees Celsius, the saturation pressure is 2.3392 kilopascal. At 40 degrees Celsius, it is 7.3851 kilopascal. So if we want to reduce the PV to increase the net positive suction head, what we should do? We should reduce the temperature. So if the working temperature is, for example, 30 degrees Celsius and it is cavitating, then you have to bring down the temperature to 20 degree or 25 or less to check and or to reduce the chances of cavitation. So this is what the understanding from this equation. So you have to understand this equation because you need to calculate the net positive suction head for your systems in several configuration, like whenever you solve any design problem, wherever you are designing it for your housing network or any place network, whether it is a greenhouse, whether it is a mall, or whether it is office network, whatever it is. Okay, so this is about the cavitation, and in the next lecture or next recording we will do the one example related to the cavitation phenomena, and you will understand more inshallah. Thank you very much.